Hey guys, how's it going? I'm back. Let me continue with the book on page 120 or 112. Okay, chapter 5 is the second example. Let us make some enhancements to the pattern finding program from chapter 4. If you recall, we wired the search pattern deep into the program. An obviously unsatisfactory arrangement following the lead of the Unix utility grep. Let us change the program so the pattern to be matched is specified by the first argument on the command line. The basic model can now be elaborated to illustrate further pointer constructions. Suppose we want to allow two optional arguments. One says print all lines except those that are match the pattern. The second says precede each printed line with its number. A common convention for C programs is that an argument beginning with a minus sign introduces an optional flag or parameter. If we choose minus lowercase x for except to sign the inversion and minus n number to request line numbering, then the command find minus lowercase x minus lowercase n, with the input. Now is the time for all good men to come to the aid of their party. Should produce the output for all good men. Optional arguments should be permitted in any order, and the rest of the program should be insensitive to the number of arguments which were actually present. In particular, the call to index should not refer to argv bracket 2 when there was a single flag argument, to argv bracket 1 when there wasn't. Furthermore, it is convenient for users if option arguments can be concatenated, as in here is the program, like this, words, so long. argv is incremented before each optional argument and argc decremented. If there are no errors at the end of the loop, argc should be 1, and asterisk argv should point at the pattern. Notice that asterisk plus argv is a pointer to an argument string. Parenthesis asterisk plus argv bracket 0 is its first character. The parentheses are necessary, for without them, the expression would be asterisk plus parenthesis argv bracket 0, which is quite different and wrong. An alternate valid form would be asterisk plus argv. Exercise 5, middle score 7. Write the program at which evaluates a reserve. Polish. expression from the command line. For example, add 2, 3, 4 plus asterisk evaluate is 2 plus parentheses 3 plus 4. Exercise 5 middle score 8. Modify the programs in tab and dtab written as exercises in chapter 1 to accept a list of tab stuffs as arguments. Use the normal tab settings if there are no arguments. Exercise 5 middle score 9. Extend in tab and dtab to accept the shorthand. In tab M plus N to mean tabs stops every n clumps starting at N and at clump M. Choose convenient for the user devote behavior. Exercise 5 middle score 10. Write the program tail, which prints the last n lines of its input. By default, n is 10, let us say, but it can be changed by an optional argument so that tail minus n prints the last n lines. The program should behave rationally, no matter how unreasonable the input or the value of n. Write the program so it makes the best use of available storage. Lines should be stored as in sort, not in a two-dimensional array of fixed size. 5.12 Pointers to functions. In C, a function itself is not a variable, but it is possible to define a pointer to a function, which can be manipulated passed to functions placed in the arrays, and so on. We will illustrate this by modifying the sorting produce written earlier in this chapter so that if the optional argument minus n is given, it will sort the input lines numerically instead of lexicographically. A sort often consists of 3 parts: a comparison, which determines the ordering of any pair of objects, and exchange, which reverses their order, and a sorting algorithm which makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations. So by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. We can arrange to sort by different criteria. This is the approach taken in our new sort. The lexicographic comparison of 2 lines is done by strcmp and swap, and swapping by swap as before. We will also need a routine numcmp, which compares 2 lines on the basis of numeric value and returns the same kind of condition indication as strcmp does. These 3 functions are declared in main, and pointers to them are passed to sort. Sort in turn calls the functions the pointers. We have skimmed on error processing for arguments so as to concentrate on the main issues, like this. strcmp, numcmp, and swap are addresses of functions. Since they are known to be functions, the ampersand operator is not necessary, in the same way that it is not needed before an array name. The compiler arranges for the address of the function to be passed. The second step is to modify sort. The declarations should be studied with some care. It says that comp is a pointer to a function that returns an int. The first set of parentheses are necessary. Without them, would say that comp is a function returning a pointer to an int, which is quite a different thing. The use of comp in the line is consistent with the declaration. Comp is a pointer to a function. Asterisk comp is the function, and like this word is the call to it. The parentheses are needed so the components are correctly associated. We have already shown strcmp, which compares two strings. Here is numcmp, numcmp, which compares two strings on a leading numeric value. The final step is to add the function swap, which exchanges two pointers. This is adapted directly from what we presented earlier in chapter. There are a variety of other options that can be added to the sorting program. Some make challenging exercises. Exercise 5, mid-score 11. Modify sort to handle a mid-score R flag, which indicates sorting in reverse decreasing order. Of course, mid-score R must work with mid-score N. Exercise 5, mid-score 12. Add the option mid-score F to fold upper and lower case together so that case distinctions are not made during sorting. Upper and lower case data are sorted together so that lowercase a and uppercase a appear adjacent, not separated by an entire case of the alphabet. Exercise 5, mid-score 13. Add the -d dictionary order option, which makes comparisons only on letters, numbers, and blanks. Make sure it works in conjunction with -f. Exercise 5, mid-score 14. Add a field handling capability so sorting may be done on fields within lines, each field according to an independent set of options. The index for this book was sorted with -df for the index category and -n for the page numbers. Chapter 6, Structures. A structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient handling. Structures are called recurse in some languages, most notably Pascal. The traditional example of a structure is the payroll record. An employee is desirable. An employee is described by a set of attributes such as name, address, social security number, salary, etc. Some of these, in turn, could be structures. A name has several components, as does an address, even as does an address, and even a salary. Structures help to organize complicated data, particularly in large programs, because in many situations they permit a group of related variables to be treated as a unit instead of as separate entities. In this chapter, we will try to illustrate how structures are used. The programs we will use are bigger than many of the others in the book, but still of modest size. 6.1 Basics. Let us revisit the data conversion routines of Chapter 5. A data consists of several parts, such as the day, month, and year, and perhaps the day of the year and the month's name. These 5 variables can all be placed into a single structure like this. The keyword struct introduces a structure declaration, which is a list of declarations enclosed in braces. An optional name called a structure tag may follow the word struct, as we stated here. The tag names this kind of structure and can be used subsequently as a shorthand for the detailed declaration. The elements of variables mentioned in a structure are called number. A structure number called members, not numbers. A structure member or tag and an ordinary i.d. non-member variable can have the same name without conflict, since they can always be distinguished by context. Of course, as a matter of style, one would normally use the same names only for closely related objects. The right phrase that determines the list of members may be followed by a list of variables, just as for any basic type that is syntactically analogous to, in the sense that each statement declares x, y, and z to be variables of the named type and causes space to be allocated for them. A structure declaration that is not followed by a list of variables allocated is no storage. It merely describes a template for the shape of a structure. If the declaration is tagged, however, the tag can be used later in definitions of actual instances of the structure. For example, given the declaration of data above defines a variable d, which is a structure of type data. An external or static structure can be initialized by following its definition with a list of initializers for the components. A member of a particular structure is referred to in an expression by a construction of the form. The structure member operator connects the structure name and the member name to set leap from the date in structure D, for example, or to check the month's name, or to convert the first character of the month's name to lowercase. Structures can be nested A parallel record may actually look like this. The person structure contains two deities. If we declare MP as struct person MP, then MP point birthday date point month refers to the month of birth. The structure member operator point associate is left to right. (6.2) Structures and functions. There are a number of restrictions on C structures. The essential rules are that the only operations that you can perform on a structure are take its address with ampersand and access one of its members. This implies that structures may not be assigned to or copied as a unit, and that they cannot be passed or to or returned from functions. These restrictions will be removed in forthcoming versions. Pointers to structures do not suffer these limitations. However, so structures and functions do work together comfortably. Finally, automatic structures like automatic arrays cannot be initialized. Only external or static structures can. Let us investigate some of these points by rewriting the date conversion functions of the last chapter to used structures. Since the rules prohibit passing a structure to a function directly, we must either pass the components separately or pass a pointer to the whole thing. The first alternative uses day underscore year as we wrote it in chapter 5. The other way is to pass a pointer. If we have declared hire date as and rewritten day of year, we can then say to pass a pointer to hire date to day of year. The function has to be modified because its argument is now a pointer rather than a list of variables. The declaration says that PD is a pointer to a structure of type date. The notation exemplified by PD arrow year is new. If P is a pointer to a structure, then P arrow member of structure refers to the particular member. The operator arrow is a minus sign followed by greater than. Since PD points to the structure, the year member could also be referred to as, but pointers to structures are so frequently used that the arrow notation is provided as a convenient shorthand. The parentheses are necessary in parentheses asterisk PD point year because the precedence of the structure member operator is higher than asterisk. Both arrow and point associate from left to right. So P arrow Q arrow member, okay, like this. For completeness, here is the other function, month, day, rewritten to use the structure like these words. The structure operator arrow and point together with parentheses for argument list and break for subscripts are at the top of the precedence hierarchy and thus bind very tightly. For example, given the declaration then increments lowercase x, not lowercase p, because the implied parenthesization is plus plus parenthesis p arrow x. Parentheses can be used to alter the binding. Parenthesis plus plus p arrow x increments p before accessing x, and parenthesis p plus plus arrow x increments p after. This last set of parentheses is unnecessary. Why? The same way. Asterisk p arrow y fetches whatever y points to. Asterisk p arrow y plus plus increments y after accessing whatever it points to, just like asterisk s plus plus asterisk p plus asterisk p arrow y plus plus increments whatever y points to, and asterisk p plus plus arrow y increments p after accessing whatever y points to. 6.3 Arrays of structures. Structures are especially suitable for managing arrays of related variables. For instance, consider a program to count the occurrences of each C keyword. We need an array of character strings to hold the names and an array of integers for the counts. One possibility is to use two parallel arrays, keyword and key count, as in. But the very fact that the arrays are parallel indicates that a different organization is possible. Each keyword entry is really a pair, and there is an array of pairs. The structure declaration defines an array key tab of structures of this type and allocated storage to them. Each element of the array is a structure. This could also be written. Since the structure key tab actually contains a constant set of names, it is easiest to initialize it once and for all when it is defined. The structure initialization is quite analogous to earlier ones. The definition is followed by a list of initializers enclosed in braces. The initializers are listed in pairs. The initializers are listed in pairs corresponding to the structure members. It would be more precise and enclose initializers for each row or structure in braces, as in. But the inner braces are not necessary when the initializers are simple variables or character strings, and when all are present. As usual, the compiler will compute the number of entries in the array key tab of initializers are present, and the bracket is left empty. Keyword counting program begins with the definition of key tab. The main routine reads the input by repeatedly calling a function getWord that fetches the input one word at a time. Each word is looked up in key tab with a version of the binary search function that we wrote in chapter 3. Of course, the list of keywords has to be given in increasing order for this to work. We will show the function getWord in a moment. For now, it suffices to say that it returns letter each time it finds a word and copies the word into its first argument. The quantity n keys is the number of keywords in key tab. Although we could count this by hand, It is a lot easier and safer to do it by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a new pointer, then move along key tab until the end is found. But this is more than is needed, since the size of the array is completely determined determined at the is completely determined at compile time. The number of entries is just. C provides a compile time unary operator called sizeOf, which can be used to compute the size of any object. The expression is an integer equal to the size of the specified yes an integer equal to the size of the specified object. The size is given in unspecified units called bytes, which are the same size as a char. The object can be an actual variable or array or structure, or the name of a basic type like int or double, or the name of a derived type like a structure. In our case, the number of keywords is the array size divided by the size of one array element. This computation is used in a hash-defined statement to set the value of n keys, like these words. Now for the function getWord, we have actually written a more general getWord than is necessary for this program. But it is not really much more complicated. GetWord returns the next word from the input, where a word is either a string of letters and digits beginning with a letter or a single character. The type of the object is returned as a function value. It is letter if the token is a word, EOF for end of file, or the character itself if it is non-alphabetic. GetWord uses the routines getch and engage, which we wrote in chapter 4. When the collection of an alphabetic token stops, GetWord has gone one character too far. The call to engage pushes that character back on the input for the next call. GetWord calls type to determine the type of each individual character of input. Here is a version for the ASCII alphabet only. The simply constants letter and digit can have any values that do not conflict with non-alphanumeric characters and EOF. The obvious choices are getWord can be faster if calls to the function type are replaced by references to an appropriate array type bracket. The standard C library provides macros called isAlpha and isDigit, which operate in this manner. Exercise 6 middle school 1. Make this modification to getWord and measure the change in speed of the program. Exercise 6 middle school 2. Write a version of type which is independent of character set. Exercise 6 middle school 3. Write a version of the keyword counting program which does not count occurrences contained within quoted strings. 6.4 Pointers to structures. To illustrate some of the considerations involved with pointers and arrays of structures, let us write the keyword count in program again, this time using pointers instead of array indices. The external declaration of key tab need not change, but main and binary do need modification. There are several things worthy of note here. First, the declaration of binary must indicate that it returns a pointer to the structure type key instead of an integer. This is declared both in main and in binary. If binary finds the word, it returns a pointer to it. If it fails, it returns null. Second, all the accessing of elements of key tab is done by pointers. This causes one significant change in binary. The computation of the middle element can no longer be simply, because the addition of two pointers will not produce any kind of a useful answer, even when divided by 2, and in fact is illegal. This must be changed to which sets mid to point to the element halfway between low and high. You should also study the initializers for low and high. It is possible to initialize a pointer to the address of a previously defined object. That is precisely what we have done here. In May, we wrote this sentence. If P is a pointer to a structure, any arithmetic on P takes into account the actual size of the structure. So P++ increments P by the correct amount to get the next element of the array of structures. But don't assume that the size of a structure is the sum of the sizes of its members, because of alignment, because of alignment requirements for different objects. There may be holes. There may be holes. There may be holes in a structure. Finally, an aside on program format. When a function returns a complicated type as in, like this, the function name can be hard to see and to find with a text editor. Accordingly, an notariate style is sometimes used. This is mostly a matter of personal taste. Pick the form you like to hold to it. Pick the form you like and hold to it. 6.5 Self-referential structures. Self-referential structures. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can't conveniently sort it and use a binary search. Yet we can do a linear search for each word as it arrives. To see if it is already been seen, the program would take forever. More precisely, its expected running time would grow quadratically. More precisely, its expected running time would grow quadratically with the number of input words. How can we organize the data to cope efficiently with a list of arbitrary words? One solution is to keep this set of words seen so far sorted at all times. by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting words in a linear array, though that also takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains no node may have more than two children. It may have only it might have only 0 or 1. When the nodes are maintained so that at any node the left subtree contains only words which are less than the word at the node, and the right subtree contains only words that are greater. To find out whether a new word is already in the tree, one starts at the root and compares the new word to the word stored at that node. If they match, the question is answered affirmatively. The question is answered affirmatively if the new word is less than the tree word. The search continues at the left child, otherwise the right child is investigated. If there is no child in the required direction, the new word is not in the tree, and in fact, the proper place for it to be is the missing child. This search process is inherently recursive, since the research from any node uses a search from one of its children. Accordingly, recursive routines for insertion and printing will be most natural. Go back to the description of a node. It is clearly a structure with 4 components. This recursive declaration of a node may look chancy, but it is actually quite correct. It is illegal for a structure to contain an instance of itself, but declares left to be a pointer to a node, not a node itself. The code for the whole program is surprisingly small. Given a handful of supporting routines that we have already written. These are get words to fetch each input word and a log to provide space for squirreling the words away. Squirreling. The main routine simply reads words with get word and installs them in the tree with tree. Tree itself is straightforward. A word is presented by main to the top level, the root of the tree. At each stage, that word is compared to the word already stored at the node, and is percolated down to either the left or right subtree by a recursive call to tree. Eventually, the word either matches something already in the tree, in which case the count is incremented, or an null pointer is encountered, indicating that a node must be created and added to the tree. If a new node is created, tree returns a pointer to it, which is installed in the parent node. Okay, guys, it is time for me to take a cup of tea. See ya.